So, in this lecture, I will mostly talk about the blow up in more general way, general definition. And smooth morphisms. So, see, recall that the way you define blow up, see, if you remember that how did you define blow up? You took, suppose you take a point P here, you can take P to be origin, and you take the projective space Pn minus 1. So, if the coordinate ring, if you denote it by k x1 x2 xn, and the homogeneous coordinate ring here, if you define it k y1 y2 yn, then you considered some blow up at a point. I think I denoted it by tilde. This is blow up at the point P. P you can take without loss of generality a point 0 at A and K. So, this you defined some closed subset in the product of these two space. One is affine, another is so this is xi yj and yi xj, I equal to 1 to n, j equal to 1 to n, right. So, this is the 0 set in the, but y1, y2, yn are homogeneous coordinates, and these x1, x2, xn's are. So, you define, and then from here you have the standard projection map, and then you will see that at the point. So, this map pi is a projection map. This is the first projection, and this pi, if you restrict to the fiber over the point, then this is a isomorphism with right, and at the point 0, the fiber is isomorphic to the Pn minus 1, right. Now, this you generalize for the for if you take some, if the point, suppose you have some subvariety y here, then you took blow up of 0 at y is nothing but you take the pi inverse of y minus 0 and take the closure inside your this A and K tilde. So, this is blow up at the points. So, if y is a subvariety, if this is a closed subset. So, this is how you define, right. Now, the one thing is, it says this construction is little low, this is a local construction, and but you can think more geometrically. This is very algebraically you can define it. Geometrically, you can give an alternate definition. So, that that is sometimes is useful to way to think. So, geometrically this A n k tilde is obtained from the plane A n k by removing the point, sometimes I call it P, this point P, and replacing it with lines passing through P basically this is a tangent space at the point P in such a way, because see Pn minus 1, these you can think as lines passing through this point Z. So you have this natural map, right? If you take the origin out, then you have the natural map to the Pn minus 1. So a point corresponds to a line passing through the point P in such a way. So at that point everywhere it is same, but at that point you are putting a Pn minus 1. It's like a bubble. But says in topology you attach a sphere. See, whenever you have some non-smooth point, a corner, to make it a smooth, what do? You make it curve, right? If you have some sharp edge, then you make it a sphere. So Pn minus 1 you can think as this is the algebraic analog of sphere. So at the point you are attaching a sphere, or attaching the projective space. So this is what such a way that the resulting surface resulting variety is smooth. I mean pictorially, for example, if you take n equal to 2, so pictorially suppose n equal to 2, so you have this say you have this picture. Let me try to draw the picture. So if I call this point P, so then I draw the axis, x-axis, y-axis. So now you have this various lines passing through P, right? So now this is the Z. Now if you draw this Z, suppose this is the Z axis. So now what you do? So now this is a XY plane. The sphere. This is A2, and you are making this will be A2 cross P1, right? So now so what you do? Every line you draw a parallel line. You think of this, but this parallel line they don't intersect. So they will be something. So corresponding to this line, you have this, and then corresponding to this line. So this is the corresponding. Now if you take this point, now this will be something like. But these two lines are in a A2 cross P1, so they don't intersect. Right, but each point you think as you draw a parallel line in the space, okay, in A2 cross P1. But at the point P, you see a line with a point in infinity. That is how you think that each line is so this point inverse image is the line which is cutting this z-axis. So at this point you have the entire P1, and other point they are isomorphic. So the surface is in this way. Now if you take for example, if you take a say singular curve, for example, if you take something like, so let's try to draw something like this. So then what you get, so this is let's make it a solid line, the z-axis. So if you take the inverse image, what will you get? You will get something like a line. So this line passing through this, right? So so it will be something like, it will go like this and cutting like this and go like this. So this point will have, so this curve is y square equal to x square plus x cube. and singularity is at the point 0. So now when you take the inverse, means that it will have two inverse, it will cut. So this is the closure. So you take the closure of pi inverse of y. This is the so pi inverse of y. If you take closure, it will intersect at 2 points. So this is a normalization, and this is a smooth curve. But if you, for example, if you take the curve something like this, you will see that this curve will be something like this. So it's a bijection. Right? So for example, if you take y square equal to x cube, which is this V-shaped curve, this curve will have it will intersect z axis at only one point. So they are bijective, but one is smooth, another one is non-smooth. But here it is not bijective. The set theory, it's not. It at the fiber at the point 0, it has 2 point. The cardinality is 2. Other points is a. So this is a geometrically. So but what is the point is that in this, so whatever is blow up of a point at x y at x, suppose P is a point here, or let's write y. See, the fiber dimension or fiber number of points in this case is going up. So in particular, here in the curve case, it is just a finitely many points. But if you take some surface, so then the fiber will be some positive dimension. So and the dimension will go up, and that is I mean, generally that is the case, that dimensions, if dimensions always go up into closure. I mean, so that's a theorem of Chevalier. I'll talk about that. Okay. When I talk about smooth morphisms. So it will come here, it will come to this. See, so important thing to notice here is that blow up at a point, at the point there is something happening, but other than that point, it is isomorphism. It's a birational map. So this map is called birational. I mean, it is birational because this is P is a closed subset, right? A point is a closed subset, and in the complement, it is a isomorphism. So it's a birational map. In particular, if you take the blow up, if you take, so I'll talk about more generally what is blow up of a subvariety. This is just blow up of a point. So in general, you can generalize this for so generalization of blow up at a point at a subvariety. Okay, so this is what you do this. So this is how do you do. So you see, what you do even when y equal to point, subvariety y inside x. X is some, say x is some a project n or pn projective space. Also you can talk about. So suppose y is a point and x is an. In this case, even, so what you do, you take this map, this natural map, ank minus your y is point, which is 0. You take this natural map, right? Now what you do, so you have this map pi, and consider this graph of pi. The graph of pi is in an cross pn minus 1. And if you take the closure of this, you see this is same as what I defined, blow up of the point. This is, you just try to think. So this way also one can define. So advantage with this, is that you can define it for projective space. For example, if you take this projective space Pn, you take the point say 1 0. So suppose you take a point. So this is say 1 0. Now from this to Pn minus 1 there is a natural map, right? Because if you take the point 1 0 0 out, then any point here, one of the other than A1, the one of the so the map is if it is A1 A2 or A0 AN, you send it to A1 AN. Now if you remove the point 1 0 0 0, then this is a well defined map, right? Because then one of these AIs should be non-zero, right? If it is all 0, then but that point you have removed. So there is a natural point, map. If you remove a point, it is like projecting to the hyperplane, right? This is a natural map. And now you can define blow up at that point, say P and K, to be you call this pi, this graph of pi closure. So this is, of course, this is in Pn cross Pn minus 1. So this way of looking at is sometimes very useful, to see blow up as graph of certain rational functions. These are rational functions basically, because this is not from the end. So this is a function from Pn. So this is on an open set, it's a map, right? So this is a rational function. You have a rational function to a projective space, to the one dimension less projective space, and take the closure. So this is another way of, so this is how you define blow up at a point of a projective space. If you can do it more generally, suppose you have a point y, now you can do the same technique. Like if the point is in y, then you consider pi inverse of y minus point and take the closure. Whether if you are in if you are in affine space, you take the closure in An cross Pn minus 1, or if you are in projective space, it's Pn cross Pn minus. So that's how you generalize, and you can generalize it more generally, like not just point. If you take some subvariety z in y, so you can define blow up of z at y. Anyway, so I will not go into much detail. So I will just restrict to points. General definition. Okay. So I will just restrict to blow up at a point. So but one can talk about blow up at a subvariety, blow up of a subvariety inside a projective space or affine space. Okay. So but see the point here, one just a remark here. In the case of blow up, so if you take this, the everywhere at x minus p and this this is a isomorphism, and at the point p, what is at the point p is the interesting thing, that what is happening in the point p. It may be the fiber. What is the fiber of at the point p? That you have to find out. Huh? Not always. It depends on x. If x is An, then it is Pn minus 1. But if it is not Pn minus, it is a closure of pi inverse y in that. So you have to see how pi inverse y is intersecting the closure. I mean, how the close, it will be on this line Pn minus 1 or line or the projective space. But pi inverse x, how that pi inverse x is sitting inside that an cross Pn minus 1, that you have to see. So, the closure of that. So, how that is cutting? For example, in this case, in one case you saw that it is cutting at 2 point. In the case of y square equal to x square plus x cube, but in the case of y square equal to x cube, it is cutting at 1 point. So, in different cases, it is different. So, the fiber you don't have much control, but the point is that the theorem of Chevalier will say that fiber dimension can only go up. It cannot be like go down. I mean, suppose the fiber in one point, the fiber is Pn minus, it cannot go down. So, that is a theorem of Chevalier. In this case, when you are blowing up at the point, because so when you have only one point, then it's nothing to do, nothing, it's just one point. But if you have a blow up along a subvariety, then for every point in the subvariety you have something. They are notorious. You don't know what is this. So, what it says that other than this y minus z, everywhere it is they are isomorphic, but at that point the fiber, when you take the fiber, the dimension will only go up, it will not drop. So, this is, I will stop here.